All right, so welcome back to Calculus. Today's plan, we're going to review a little bit about the derivatives of logs and exponents. And then I'm going to show you a great trick that we can use for differentiation using logarithms. Basically, it's going to make it so we don't have to do things like quotient rule, product rule, and certain chain rules. You'll understand when we get there. So we're going to do that and then to sort of see how things are looking. Basically, we're wrapping up chapter 3, which is how to differentiate. Excuse me. And we're going to be moving into chapter 4, which is all about applications. So you're going to start seeing why we actually care about this. But as always, before I do that, are there any questions, any homework, anything like that we need to talk about first? All right, well, seeing none, then I'm going to go ahead and hop up to the whiteboard. I'll be right back. Actually, I just saw, nope, not too late, errors. I happened to see that before I strayed too far. So you wanted to see number 8 from section 3.8. I think we can definitely do that. Just letting you guys know something's wrong with my computer today. It thinks I keep hitting the shift key, which of course means every time I click on anything in my browser, it pulls up a new window. So we'll see how this goes, but we can definitely go take a peek at that. All right, and number 12, let me put this down on my list. All right, so 3.8, numbers 8 and 12. All right, well, let me go ahead and share my screen here. All right, so hopefully you guys are seeing the, excuse me, the assignment page. So let's go see 3.8. All right, so while we're waiting on this, let's see, we need a bad joke for today. Okay, here's another train joke for you. Pretty sure I already told you the struck by lightning one. So how about this? Why can't a locomotive sit down? Because it's got a tender behind. Okay, and if that made no sense, that's because the car that's right behind the locomotive, the one that oil or coal or whatever, is called a tender. Yeah. You're welcome. All right. So, well, that bought us enough time, at least. Here we are. So for 3.8, number 8, we've got square root of x plus the square root of y equals 11. We know y of 4 equals 18. And we want to find, equals 81. And we want to find the derivative at 4. All right. And it says by implicit differentiation, We don't necessarily need to do implicit differentiation because we could solve this equation for y and then do it explicitly. But we'll see that doing this with implicit differentiation is a little bit faster. All right, so let's go to a whiteboard. All right, so we've got square root of x. Whoa, what was that? It's not look much like a square root. Let's try that again. Square root of x plus the square root of y equals 11. We were told y of 4 equals 81, and we want to find y prime of 4. All right, so let's go ahead and differentiate implicitly, which just means we're going to differentiate each side of this equation with respect to x. So everything that's not y, we treat like normal. And anything that's y, we differentiate like normal, but make sure we attach on a y prime. Okay, so to help us differentiate these square roots, let's remember that those are 1/2 powers. So x to the 1/2, its derivative is going to be 1/2 x to the minus 1/2. So that's what we would do every time if we were differentiating. Okay, so then the square root of y, same thing. It's going to be 1/2 y to the minus 1/2. But then we need to multiply that by y prime. So why is it that we have to by y prime? What's the reason behind that? Is it just nobody remembers?
Does it have to deal with implicit differentiation?
Well, yes. I mean, implicit differentiation requires it, but the real reason, kind of where I'm going for this, is not because we have to, but it's because of the chain rule, right? Y is a function that's inside another function. It's composition. So when we differentiate that, we need the chain rule. And the chain rule always says differentiate the outside. So that was this piece. And then multiply by the derivative of what's inside, which is your y prime. All right, so that's the derivative of the square root of y. And then we differentiate 11. And of course, 11 is a constant, so its derivative is 0. All right, so before we go any further, we good with this? The derivative is all right? Thumbs up? All right, so now let's use the fact that we know our point to find y prime of 4. So we've got x is equal to 4. So we're going to have 1/2, 4 to the minus 1/2. At 4, we also know y. The y is 81. So that's going to give us 81 to the minus 1/2. Y prime we don't know, but we will calculate that here in a second, because we now have an equation that just has y prime. All right, so now we need to calculate this stuff. First things first, I'm going to multiply everything by 2. Because if I multiply everything by 2, that's going to get rid of those halves. So I've got 4 to the minus 1/2 plus 81 to the minus 1/2 times y prime equals 0. All right, so the 4 to the minus 1/2, that's the same as 1 over the square root of 4. The 81 to the minus 1/2 is 1 over the square root of 81. The negative drops us down, and the 1/2 gives us a square root. All right, and so those we can calculate. Let's see, Fenry, can I just change the original function to y equals 11 minus square root of x squared to find the derivative of y? Yes, you can. This one did ask us specifically to do it with implicit differentiation, which is why we're doing it with implicit differentiation, but you absolutely can do that. I'll just warn you, like on a quiz or exam, if I tell you use implicit differentiation, you need to be able to use implicit differentiation. All right, so now let's evaluate these. So square root of 4, of course, is 2. Square root of 81 is 9. And now it's just a matter of solving this guy. And I believe that gives us y prime equals -9/2. So we know that the derivative at 4 is -9/2. And you know what, just for the sake of seeing how this plays out, let's do it explicitly. Let's solve it for y and then differentiate. So we got to square both sides. So that gives me 11 minus square root of x squared. So let's do y prime. So y prime, we're going to have to do chain rule. We're going to get 2 times 11 minus the square root of x times the derivative of what's inside, which is going to be a -1/2 x to the -1/2. The 11's a constant. The minus gives me the minus, and then this is x to the 1/2, so 1/2 x to the -1/2. And at this point, we could plug in 4. Let's see here. So the square root of 4 is 2. 11 minus 2 is 9. 9 times 2 is 18. That 4 goes onto the bottom as a square root. That's another 2, so that's a -1/4, which, hey, look at that, gives us exactly the same value. So in reality, like if all it's coming down to is we're trying to find this derivative, whether you do it implicitly or explicitly, it doesn't really matter because we get to the same place, right? However, sometimes implicit is way faster and way easier when trying to solve for y is kind of impossible. All right, so was that good for whatever number this was, number 8, I believe? All right, okay, so let's go look at the other one was number 12. So let's go see what that does for us. So we'll go back to the homework window here. And let's take a look at number 12. All right, so it says the volume of a right circular cone of radius x and height y is given by v equals 1/3 pi x squared y. Suppose that the volume of the cone is 48 pi cubic centimeters. Find dy dx when x is 4 and y is 9. Whew. Okay. Before we dive into this, let's just talk about what's going on and what all the different things are. So again, since x is the radius and y is the height, dy dx, that's looking at how does the height change as the radius changes. So if we've got a set volume of a cone, and we start changing the radius of it, the height is going to change, right? As the radius gets bigger, the height's going to have to go down. If the radius gets smaller, the height will go up. And really what we're calculating here is how quickly is that height changing with changes in the radius. So that's what this is actually asking us to do. So let's see if we can figure out this number. All right, so I just wrote down all my important information. Let's go to the whiteboard. So I'm going to clear all this stuff and we'll start anew. And I actually just had a thought, and I have no idea. I'm just curious. When you guys see my whiteboard like this, do you see the little pencil icon?
Yeah.
Yeah? Okay, cool. Because I use it to point a lot, and it just dawned on me that that might be something that only I see. So I'm glad you guys see it. All right, anyway, thanks for that. Okay, so we've got this volume. They tell us that the volume, the formula for it, right, is 1/3 pi x squared y, but they tell us that the volume is 48 pi. So we know that the relationship between these things satisfies this equation. Let me go ahead and just simplify this a little bit before we go further. I'm going to cancel out the pi's, and then I'm going to multiply by 3 just to move that over. So we get 144 equals x squared y. Excuse me. So however x and y are related, it's x squared y is always equal to 144. All right, so we want dy dx. So let's go ahead and implicitly differentiate this. We'll do a d dx. So on the left-hand side, the derivative of 144, of course, is 0 because it's a constant. And what do we have to do on the right side? What is the derivative of the right side?
Two x times y prime.
Okay, so 2x times y prime, and Ollie just typed the same thing in there, so she's on board with you, Susanna. Unfortunately, that's not correct. Because what we have to do here is, yeah, Era's just put it in the chat box. Product rule. Remember that there's really a times there. So we have to set up the product rule. So x squared, its derivative is going to be 2x. Y, its derivative is y prime. So then we do the old multiply one by the other business. So we're going to get 2xy plus x squared y prime. So I know I mentioned this last time, and I mentioned it the time before, and I'm going to continue mentioning it. Watch out for that. This is where the majority of your mistakes are going to come when you do implicit differentiation, is you're going to forget product rule. Right? Y is a function of x. X squared is a function of x. They're being multiplied together. So we have to make sure we use product rule. So I'm going to go ahead and solve this for y prime. We don't have to do that here. We could just start plugging in numbers, but I just want to, I guess. So we get y prime is equal to minus 2y over x. So if we want to find this rate of change, all we need to know are x and y. But they told us, right? They told us that we wanted to look at it when x is equal to 4 and y is equal to 9. So if you just plug those in, you get negative 18 over 4 or minus 9 halves. All right, so again, let's interpret that number. So remember, this is dy dx, which was the change in height with change in radius. All right, so first and foremost, it's a negative number. So negative number means that this height is decreasing. Well, that makes sense, right? For a cone of fixed volume, if the radius is getting bigger, the height has to be decreasing. So the fact it's negative feels good. The negative 9 halves, well, that is what it is. So negative 4.5. Basically, it's saying at that instant, for every inch the radius increases, the height is going down 4.5 inches. Every centimeter, well, I don't remember what the units are on this, but let's just call it whatever. So every centimeter it increases in radius, the height decreases 4.5 centimeters. But remember, that's an instantaneous change. So if we were to increase the radius by a whole centimeter, we'd see a different change in the height. But instantaneously at this moment, that's what we've got. All right, well, this is another one. We don't have to use implicit differentiation. We could have done it explicitly. Let me just show you real quick. So slide over here. If instead I had taken this equation and solved it for y, I get y is equal to 144 over x squared, or also known as 144x to the minus 2. The derivative of that would be minus 288x to the minus 3, or negative 288 over x cubed. Again, we could plug in our x equals 4. So we get negative 288 over 4 cubed. And that actually will also go down to negative 9 halves. So get the same thing either way. Now, this is one where explicit differentiation is way easier, right? If you look at the calculus step, there was one calculus step, and it was right there. That calculus step was just simple basic power rule, as opposed to the calculus step here, which required product rule and remembering implicit differentiation. So this is a circumstance where if you recognized it, you'd probably want to do it explicitly. But if you don't recognize it, that's fine. You can still use implicit differentiation. All right, so how about this for number 13? We feeling better about that?
I have a question. There was a step that you said that you didn't have to do, but you were going to do it anyway. Was that when you solved all the way for y prime?
Correct.
Because you could have just plugged in the numbers at which step?
Right here. If instead I had just gone, okay, let's plug in x and y. So we have 2 times 4 times 9 plus 4 squared times y prime. I could have just shoved all those numbers in right there, which would have given me 0 equals 72 plus 16 y prime. And then solving for y prime would have given me negative 72 sixteenths, which reduces down to minus 9 halves. So I didn't actually have to write y prime equals. I just did it because, well, because I'm used to getting y prime equals. But for this one, since we have specific values, it's not necessary. Does that answer your question there, Alia?
Yeah, thank you.
Okay, you're welcome.
Would you say that's something that's good to get in the habit of doing?
I don't know about. I don't know. Because it really depends on what the question is asking you. I think the reason I go to y prime, just y prime equals, is no matter what you're being asked to do, y prime equals covers it, right? Because like if it says find an equation for dy dx, or you're not given a point and it just says find dy dx, then that would be our answer, right? This would be our dy dx is minus 2y over x. Because you're not always given a point. I don't like the questions that are like, is this something that we should just get in the habit of doing or whatever? I really don't like giving blanket answers to that, because even for me, it depends. I mean, there are times when I don't solve for y prime, when I do just plug the stuff in and go if I have a specific point. I think this one I did it because I realized it was going to be really easy and was going to simplify down nicely. So even for me, it's depends on my mood at the time. Depends on how much work I'm willing to do. Is this equation worth doing it? Blah, blah, blah. So I don't know that I'm actually going to answer that question. So I hate to disappoint you there, Tim, but it's a good thing to recognize that you can do. And it's good to recognize when you need to do it. But I'm not going to advise one way or the other of it's something you should just do and get in the habit of. So let me preach a little bit more. So math, and this is something that most people don't really think or recognize, but math is like so many other things that it's a very personal experience. And as soon as I said that, I know some of you started like in your mind shaking your head or was like, what? It's a personal experience. But it is. You can craft math and you can do math in a way that best suits you as a person. We're taught as youngsters that math is do these steps this way, do it this way, always get to your answer, right? Like when you learned multiplication, there was a process for doing multiplication. When you learn factoring, there's a process for factoring, right? So we kind of get trained to think that math is just you do these steps. But as you go further, and I'm sure you're starting to see it, that we can be presented with a problem like this one. And already, I mean, even on the whiteboard, right? Look, there are two distinct ways that we did to get to the same place, both equally valid, both work just fine, but they're different. And that's just like a minor example. And so because it is so personal, to get good at math, you know you're good at math when you quit looking for the recipe. When you quit looking for these are the steps every time I do it this way, right? And that's okay. It's okay to have that. But when you can move beyond that and go, ooh, here's a problem. And you can recognize, I can go this path, I got that path, I got like 4 different paths. And you start finding the one that works best for you. That's when you get good at math. So my advice with this stuff is start looking at recognizing the multiple paths. Start trying to picture a couple steps ahead down each path, because sometimes you can look at it and go, like in this case, oh crap, if I do implicit differentiation, I'm gonna have to use a product rule. If I do it explicitly, it's a simple power rule, right? So just keep in mind that there are more than one way. Obviously, in exam situations, because it's manufactured and I'm looking for, do you know how to do the specific types of things? I'll ask you, right? Like I'll say, do this limit algebraically, or use implicit differentiation, or, you know, whatever I'm trying to test you on. But out there in the real world, when you're actually doing this, it's huge. And to be able to look at something and recognize that there's more than one way and find the way that works best and easiest for you. And I think the point I'm trying to make is that you're not me. We're different people. And so we're going to approach things differently. We're going to think about things differently. And so when I'm asked, you know, like by you, Tim, there's like, is this the way I should do it? My answer is always like, there is no should. There isn't. Like if someone asks me, how am I supposed to do, you know, how should I do this? I go, in such a way that you get the right answer. It's a very unfulfilling response, right? You're just like, well, thanks for nothing. But it's true. Like, how do I want you to attack one of these problems? Yeah, in whatever method gets you to where you need to be. I don't care, right? I'm not one of those people that's like, well, I showed you, you have to do it, because that's nonsense, right? Because you're not always going to have Bruce looking over your shoulder, making sure you're doing it the right way, right? You're going to start doing this stuff on your own. Make it yours. Own it. I mean, it's like art. I could teach you about how to paint, right? You could take an art class with me. That would be a horrible class, by the way. But you could take an art class with me and I could tell you, okay, well, we're going to paint trees and, you know, here are brush strokes and this is how you mix colors and stuff. But when it comes time for you to actually draw your trees, to paint your trees, they're going to look completely different than anyone else's in the class, because you are an individual. And same kind of thing can happen in math. And I know, again, a lot of you are probably like, dude, what is this guy smoking this early in the morning talking about this and comparing it to art and all that? But math it's an art. It really is an art. And what I'm doing is teaching you techniques. But then you need to take them and produce your own artwork. So anyway, I'm done preaching. And I know that was probably a really unfulfilling answer to Tim's question, which is, should you do it this way? I don't know if you feel like it, which is a horrible response, but that's what I'm going to give you. Are we good? Anything else, or shall we move over to the whiteboard? All right, so hearing nothing else, I'm going to go ahead and hop on over. So I will see you guys in just 1 second. All right, so let me just remind you about where we left off last time, which was with exponential and logarithmic functions. And so we have the two groups that we now know their derivatives, right? So if we've got exponential functions, f of x equals a to the x.
Yes, how do you
let me. All right, when all else fails, turn it off and back on again. How about now? Can you hear me better? About the same. All right, hold on 1 second here. Okay, so I just switched to my Bluetooth. Is that better? Worse? Same? All right, we're better. Okay, we'll go with this. Let me know again if things change, but thanks for informing there. All right, so exponential functions, f of x equals a to the x. We just know that a has to be greater than 0 and not equal to 1. But last time we evaluated the derivative. And does anybody remember what it looks like? What the derivative of a to the x is? So maybe this is when people are frantically looking back in their notes. But it turns out that it's just a multiple of a to the x. It's just the natural log of a times a to the x. So whatever your base is, you take its natural log and you multiply it by the original function. And what we saw, like for example, here are a few. We could have, say, y equals 3 to the x. So y prime is the natural log of 3 times 3 to the x. Boom, done. Or y equals 1/2 to the x. Y prime is natural log of 1/2 times 1/2 to the x. It really is that easy. But the best one by far is e to the x. Because this guy, if we differentiate, right, we're going to get natural log of e times e to the x. But the natural log of e is just 1. So if y is e to the x, then y prime is e to the x. So you're going to like e to the x. It's by far the best function out there when it comes to differentiation, because when you differentiate it, it's just itself. Okay, so these are exponential functions. I do want to warn you, though, it's really easy to get these confused with polynomial functions, with power functions, right? Like y equals 3 to the x. It looks a lot like y equals x cubed. But of course, that one has a very different rule, right? That one, of course, we're going to get 3x squared because we're using power rule. So be careful when you're doing these, because there is the tendency, when you've got something like 3 to the x, to try to use the power rule. Bring the x out front as a multiple. Decrease the exponent by 1, but it's not the same. Notice that it all comes down to where the variable is. If the variable is the exponent, right? If the variable is up there in the power, it's going to be an exponential function. If the variable is the base, then it's power rule. All right, so just watch out for that. That's something that students will sometimes fall into. All right, so those were our exponentials. Nice and easy. All right,
And then we did the same thing. We developed the rules for logarithms. And so if we have another function that's log base a of x, then its derivative is a fraction, and it's 1 over natural log of a times x. So that's the derivative for logs. So let me just show you a few of these. And again, they're nice and simple. It's just a matter of using that rule. So if we've got, say, y equals log base 5 of x, then y prime is going to be 1 over the natural log of 5 times x. Or if we have y equals log of x, I think I showed this to you last time. I just want to remind you that if we don't write a base, it's implied that it's base 10. So y prime is going to be 1 over the natural log of 10 times x, and so on and so forth. But again, the nice one is natural log. Because if we've got y equals natural log, then y prime is 1 over the natural log of e times x. And again, just like with the exponential, the natural log of e is 1. So that guy's just plain old 1 over x. So just like e to the x is nice, natural log of x is nice, because its derivative just ends up being 1 over x. Okay, so not a big deal. They're pretty easy rules. It's just one more that we have to remember. All right, so far so good. Kind of coming back. And so then the last thing I showed you last time was, what if there's something more complicated in a natural log? And so this is going to be sort of another rule, just in general. If we've got f of x equals the natural log of u, so u is some function of x, then f prime is actually equal to u prime over u. So I guess I would call that, say, the general log rule. So if you've got log of stuff, the derivative is just the derivative of that stuff over the stuff. So I think I showed you some examples last time, but we'll do a couple more here just in case. So for example, let's say y is equal to the natural log of e to the x plus x. Then y prime. All right, so here's what you do. You take what's inside, you put it on the bottom. So there's going to be an e to the x plus x on the bottom. And then on top, we take the derivative of what's inside. Well, e to the x, its derivative is e to the x. The x, its derivative is 1. So if y is equal to the natural log of e to the x plus x, its derivative is e to the x plus 1 over e to the x plus x. And it completely doesn't matter what's inside of that log. We always do it the same. So how about we have x cubed plus tangent of x minus 4 in our natural log. Okay, so we've got natural log of x cubed plus tangent x minus 4. This is how fast and easy it is. Take that function, put it on the bottom. So x cubed plus tangent x minus 4. On the top, put the derivative. So we get 3x squared plus secant squared, the derivative of tangent of secant squared, and minus 4 equals 0. So I just noticed in the chat box, Ollie just asked, what did I call these first two rules? And I'm guessing this is what you mean by the first two rules, the ones over here on the left-hand side. Yeah, they don't have a name. It's the derivative of exponential functions and the derivative of log functions. There's no name for it. It's kind of like if I told you when we wrote the derivative of sine as cosine, we didn't have a name for that because it was just the derivative of sine. Same deal here. This is just the derivative of exponential functions. This is the derivative of log functions. I just called this the general derivative because I'm allowing for anything on the inside. So anytime you hear somebody, well, me specifically say general, but this is true in math in general, is a general rule is just, it's generic. We're not specifying anything. So I'm just specifying I've got a log, not what's inside of it. All right, so hopefully you're seeing that these aren't that bad. And in fact, logs are really fast, even when you've got stuff inside, because the chain rule just makes it so that you've got the derivative of that stuff on top of the original function. Okay, so this is where we were. Are we feeling pretty good about that, kind of coming back? Thumbs up. All right, I'm seeing some thumbs ups. Awesome. Yeah, go ahead, Ollie.
The last one you were looking at, the general log rule, does that just work for natural log or for log as well?
Okay, so this is for natural log, it's just u prime over u. What would change if it was a different kind of log? What happens if our base isn't e? Well, come back and look at this, right? What this says is that if our base isn't e, we have to have a natural log of the base on the bottom. And that's the only thing that would change here. So if this was like log base 2 of e to the x plus x, we'd still get this, but we'd need a natural log of 2 on the bottom. Or if it was log base 1/3, there'd be a natural log of 1/3 on the bottom. So this exactly only works for natural log. But if it's a different base, you're only off by that multiple of the natural log of the base. Does that answer your question? Yeah, okay, cool. All right, so this is where we got last time. Everything is cool. They're not that big of a deal. It's just 2 more functions to add to our list that we know derivatives for. All right, however, this guy right here, this log 1, oh my God, is going to be your best friend. It's going to be your best friend when you get things like this. This one's not even that big of a deal, but what if this is our function? I want to know what is the derivative of y equals x to the x. That's not that bad. X to the x.
Is it a fraction where x is the denominator as well as like x prime?
Okay. So
I don't know if that sounds
this,
horrible, but
so think about it. You look at it and you go, all right, is it an exponential function? I mean, that's the question. Is it an exponential function? Is it one of these guys? Because I think, let's see. So Bailey just put in natural log of x times x to the x, which would suggest that it's this form, right? Because if we've got a to the x, we saw its derivative would be natural log of a times a to the x, but let a equal x. But here's the problem. That base right here, x, isn't constant. It's a variable. Over here, this has to be a constant base. So it's sort of exponential, but it's not. But then you go, okay, well, is it just a power rule kind of deal, right? X to the n. We know what to do with those. Bring that out front, decrease the exponent by 1, and isn't that what we've got? X to the n. Well, it's the same issue. That n isn't constant. That exponent isn't constant. So this is neither an exponential, nor is it a power rule. So that's when we go, all right, fine. We throw our hands to the sky and just go, never mind. We'll walk away. No. We're mathematicians. We don't think like that. Mathematicians, we think like, oh, you are trying to trick me. You're trying to give me something that I can't differentiate. I'm going to figure it out. I'm going to figure out a way. And mathematicians did. They did figure out a way to differentiate this. And here was the trick. That x to the x I really don't like. I don't want variables raised to other variable powers. So here's what we're going to do. We are going to get sneaky. We're going to bring that exponent. We're going to move that exponent so it's no longer an exponent. And the way we're going to do it is by using a log. I'm going to take a natural log of both sides because I can. I know that natural logs are 1-to-1, so I can do this to both sides of the equation and still be good. Now notice what happens. I still have natural log of y on the left. I don't really care about that. That's not going to be a big deal. But look at the right. The right now, I can bring that exponent out front as a multiple. So rules of logs let me do this. Now look at that right-hand side. X times natural log of x. If I said find its derivative, can you do it?
Yes.
No, so I'm not asking what it is, but can you do it? Right. So Mariel is giving me a thumbs up. What do you guys think? Is this possible to take the derivative of that right-hand side? And I'm seeing more thumbs up. Good. I know sometimes when I ask questions like this, people are like, oh, he's trying to set a trap. No,
I don't know if you can move the
trap.
x in the front though. The
Oh,
coefficient.
I know. I absolutely can move the x to the front. That's the rules of logarithms.
No. Like, I don't know what you're going to do with that one if you want us to find the derivative of x natural log x.
Oh.
Like, I know how to differentiate like them separately, but
Okay,
like differentiate them together.
Okay, so Suzanne, you say you can differentiate each individually, right? Derivative of x is 1, no big deal. Derivative natural log of x, 1 over x. Can anybody answer that question for her? What are we going to do with the x out in front?
You have to use product rule again.
Yeah, there's going to be product rule. I've got x times natural log of x. I know how to do product rule. You know how to do product rule. And so since we can do each one individually and multiply together, totally we can differentiate that. So notice what just happened. By using natural log, we turned it from a form that we can't differentiate, x to the x, into a form that I absolutely can. So I'm going to want to differentiate that, which means I need to differentiate the other side as well. So we're going to do a d dx now to both sides. All right, so let's look at the left. The derivative of natural log of y. What's that going to be when we differentiate with respect to x? Well, guess what, folks? Yep, there it is, there. It's going to be y prime over y. This is implicit differentiation. Remember that stuff we were just doing? Right? So we're going to get implicit differentiation. So we're going to get y prime over y. That's this. That's the general power rule. Instead of u, it's y. So we've got y prime over y. The other side, we need to do the product rule. All right, now, just so you guys know, I'm going to quit writing out product and quotient rules with the functions and do a little crisscross thing. Okay, we're going to start speeding this up. If you still need to do that, but I'm going to go. All right, so, and I just got notification, my earphones just went boop, boop, which means my power is dying on this. So we're going to go as long as we can. When it dies, we'll assess how audio is, but let's see how far this goes. All right, so derivative of the first one is 1. So we get 1 times natural log of x plus x times the derivative of the second one, which is 1 over x. So we're at y prime equal, or y prime over y equals natural log of x plus 1. All right, so let's go ahead and solve this for y prime. So y prime is equal to y times natural log of x plus 1. All right, so we're actually really close to being done. The only thing I don't like about this is that my derivative has y in it, but I know what y is. Even though we used implicit differentiation here, I know what y is. Y is x to the x. So I'm going to take x to the x. I'm going to drop that in here. So the derivative of x to the x is x to the x times natural log of x plus 1. And so there you go. There is the derivative of x to the x. And you notice that it does not follow power rule, not even close. It also doesn't follow exponential rules, not even close, because it's its own creature. All right. So we just use logs to help us turn this into a form that we could differentiate. And you're going to need to do this anytime you have a function of x raised to another function of x. This was a really easy one. It was just x to the x. But let me show you that even if it's a little more complicated, you can use the same process. Okay, but before I do that, any questions on this one? Anything still out there that you're not sure about? All right, so here's another one. Let's say we've got y equals sine of x raised to the cosine of x. So sufficiently ugly, right? Well, let's start by taking a natural log. Y equals cosine of x times the natural log of sine of x. Right, the rule is bring that exponent out front as a multiple. But now we're ready to differentiate. So the natural log of y is going to give me y prime over y. The other side, I need to use the product rule. All right, so the derivative of cosine is negative sine. That's going to be times the natural log of sine of x, plus cosine times the derivative of natural log of sine. Well, the general rule for logs says put what's inside on the bottom and put the derivative of what's inside on the top. So that's cosine of x. All right, so there's the product rule. And now I need to solve for y prime. So y prime is going to be all of this stuff, negative sine of x times natural log of sine of x plus cosine squared over sine of x times y. Well, let me bring that y back in. That was sine of x raised to the cosine of x. So not pretty at all. I'm not even going to pretend. But that there in the green box is the derivative of sine of x raised to the cosine of x. Okay, so moral of the story here. We have all kinds of tools at our disposal. And logarithms, we've already seen logarithms can simplify stuff down, right? Instead of powers, it turns into multiples. Instead of multiplying, it turns into add. Instead of dividing, it turns into subtraction. All of those are going to be easier to differentiate. So sometimes taking a log of both sides is well worth your time and your effort. All right, so if you ever have a function of x raised to another function of x, take a log of both sides and then differentiate. All right, so questions on this guy before I show you some other tricks with logs. No? Okay, now these two, the x to the x and the sine x or the cosine of x, those were both things that we could not differentiate otherwise. I want to show you some that we can differentiate, but by using logs makes it easier. All right, so let me write up an example here and we'll walk through it. All right, so here's another one I want. Let's find the derivative of this guy. All right, so here's your function. Y equals 3x squared minus 4x plus 1 to the 5th times 2x to the 5th minus x to the 4th plus 3x minus 4 to the 6th divided by the square root of 5x cubed minus 2x. So I'll give you a second to write that down. All right, now, can we differentiate that?
It would look very long.
Okay, it's
But
probably
it's
going to be long,
possible.
but it's possible. All right, let's just go with, is it possible? Yes. What are we going to have to do to differentiate it?
Move
What
the
rules are-
exponents to product quotient rule and product
Okay.
rule.
So Susanna's starting to freak out a little bit. We can hear it in her voice, right? But yeah, there's quotient rule for sure, because there's division. There's product rule because we have multiplying on top. We're also going to need to change that square root to a half power, right? There's going to be chain rule because we have functions being raised to power. So a general power rule, I guess, if you want to call it that, but there's chain rule, right? So this one problem would require product rule, quotient rule, and chain rule. Basically so we have quotient rule. Within that quotient rule is product rule. Within that product rule is chain rule. Right? So it would be huge, long, big process, but doable. All right, but we're going to play the same trick that we just did, which is we're going to take a log. And I saw, I think Era's put that in the chat box, said, take a log. Watch what happens if we take a log. So I'm going to start by taking a log of both sides. I'm going to need more space, so I'm going to stretch over here a bit. So we've got the natural log of y. That's going to equal. Now remember our rules of logs. When we have multiplication, division, it gets a positive log. Things are being divided, get a negative log. And at the same time, powers can come out front. So I can write this as 5 natural logs of 3x squared minus 4x plus 1 plus 6 natural logs of 2x to the 5th minus x to the 4th plus 3x minus 4 minus 1/2 natural log of 5x cubed minus 2x. So these first two are plus logs because they came from the top. This third one's a minus log because it came from the bottom. And the numbers out front, 5, 6, and 1/2, those are the powers on those pieces. Remember, square root is a 1/2 power. So rules of logs expanded it out. All right, now let's differentiate. Okay, so we're going to do a ddx of each side. Now I'm really going to expand. I'm going to start way over here. So natural log of y gives me y prime over y. The other side, let's use log differentiation. So the 5 is a constant multiple. It just sticks around. But now this natural log, I put what's inside on the bottom. So 3x squared minus 4x plus 1. And then on the top, I put its derivative. Well, its derivative is 6x minus 4. Okay, then we move to the next piece. There's a 6 as my multiple. The fraction, the bottom's going to get what's inside. So 2x to the 5th minus x to the 4th plus 3x minus 4. The top gets its derivative. 10x to the 4th minus 4x cubed plus 3. All right, now we move to the next piece. It's going to be minus 1/2 times, same deal. It's a log. So the bottom gets what's inside. The top gets its derivative. And there you go, ladies and gentlemen. We are done differentiating. I don't know if you quite see.
That doesn't look very clean. I don't know.
Well, it wasn't going to
like,
look clean anyway, right?
Yeah, but I feel like you could do something with the multiplication coefficients, but I'm not sure what you can do.
Well, okay, you can combine these.
Yeah, that's what I was thinking.
You can add the fractions
Okay.
together and all that. You're jumping the gun on me a little, Susanna. Let's just talk calculus.
Oh, okay.
That's all algebra. And algebra from here on out is algebra. But look at the calculus involved. So just think differentiation. How hard was this differentiation step?
Not that bad, actually.
No, it was
not really easier than I thought it would be.
Okay. And it is easier because we took a log. Mm-hmm. Had we not taken a log, it would have been
extremely long.
With product rule inside of it, with chain rule inside of the product rule. But by taking a log, we just made the calculus fast. So Ollie just said, isn't it a problem that the y is still remaining? Yes, we'll take care of that in a second. But again, I just want to talk calculus for a second. The calculus was easy. The differentiation was fast because of the general log rule. Now, we are not done because we still need to get y prime by itself, which means we got to move this y. But in terms of the calculus, taking a log make calculus quick and easy. All right, well, if I wanted to finish this, this is what I'd have to do. So y prime is going to equal all of this stuff. Let me just rewrite it real quick. All right, so that was all that side, but now I have to multiply by y. Well, let's take our original y and put that over here. All right, so there it is in all of its glory. There is the derivative of what we started. And yes, it is ugly. And yes, it is long. And yes, it is, insert your favorite descriptor of how horrible and nasty this looks. Because it does. It looks horrible. But think like a mathematician. Does a mathematician care what it looks like? No. All the mathematician cares about is, can I do it? Done. I found the derivative. And now let's say you told me, all right, well, find the derivative of this thing, find the slope of the tangent line at x equals 0. No, don't go x equals 0. It's undefined. At x equals 1. All right, well, now I'll plug in x equals 1. And I'll get a number. And that's my slope. That's my rate of change. And now I can use it to do whatever I use derivatives for. I don't want you to look at the end of this and fixate on the end. Please do not. Don't look at this and go, oh my God, this is the ugliest looking thing in the world. This is horrible. Don't think about it that way. Think calculus. Think the calculus steps. This was awesome because calculus was easy. Yeah, we had some algebra we had to deal with, whatever. But the calculus, because of the fact that we used logs. I don't think any of you had me for a pre-calc class where I taught logarithms, because I don't think I've taught that pre-calc for a while. But one thing, when I talk logs, and people are always like, why do we care about the rules of logs? They're silly, they're blah, blah, blah. You know, I give them the history, and historically they were awesome. Like without calculators, the rules of logs made things so much easier to actually calculate and do stuff. So historically, yeah, they were great. And then I tell that to students, and students go, well, that's great and all, but I've got, you know, my phone that's got a built-in calculator that knows this, and I don't need to blah, blah, blah. And I tell them, yeah, they're still really useful. You'll see when you get to calculus. And this is what we're talking about. This is why we care about the rules of logs still today, is it makes it so that we can do these computations much faster. Still ugly. But I'll do that. Do me a favor. If you're fixated on this and you're going, oh my God, this is ugly, I hate this derivative. Do this derivative the other way without logs. Do the quotient rule that's got the product rule inside of it, that has chain rule inside of it. Just do that. See how you like it and compare it to what we just did. Your answer, by the way, is not going to look much prettier than this. It's going to be slightly different because, you know, we could do algebra and distribute and stuff like that, but you'll get an equivalent form. It's still going to be ugly as hell, but you're going to have worked way harder to get there than with the logs. So we call this logarithmic differentiation. This process of taking a log of both sides and then differentiating. And it can be really useful when you have a bunch of multiplication and division and powers, because the rules of logs let you split those things apart and do this much quicker. So I'm going to show you another example, but I want to give you the opportunity to ask any questions on this before I erase it. Because once I erase it, we're never seeing it again. I'm not going to be able to reproduce it. So if you've got any questions, let me know before I kill it. All right. I hear none, I see none. It's going away. All right, so here's another, let's do another function that we want to get the derivative for. And let's say that this one is y equals, let me throw in some other stuff here because we've just been doing polynomials. Let's say we've got natural log of x plus 4 over e to the x minus secant of x. And that's going to be all raised to the 10th power. So if we go to the always question that I asked, differentiate this as it is. And the answer is yes. It's going to be general power rule, right? We got stuff raised to the 10th. But that stuff being raised to the 10th is going to require quotient rule and yeah. Okay, so we could do it as it is. But instead, let's do so I'm going to pause here for a second. My Bluetooth just died, which means I should be back onto this audio. Can you hear me okay?
Yeah, it's fine now.
Yeah, we're good? All right. I can't hear you, but now I can. All right, so let's take a derivative of both sides. Or not a derivative. Let's take a log of both sides. So we're going to get the natural log of y. Now let's start breaking this thing down. So I've got a power of 10. That 10 is going to come out front. I'm actually going to show you the steps of the log expansion here. So that power comes out front as a multiple. And then I have division on the inside. So I'm going to be able to split that apart as subtraction. Okay, so that power came out front. I did that first because the entirety was being raised to the 10 power. Then this piece with the division got split into the two subtractions. So before we differentiate, are we good with what the logs did for us? Thumbs up. Okay, seeing lots of thumbs up. Good, good, good. All right, so now let's differentiate. So now we'll do the d dx. All right, so the natural log of y, we're going to get y prime over y. The 10 is a constant multiple, so it's just going to stick around there. The derivative of natural log of x plus 4. So the stuff that's on the inside goes on the bottom. And then we take a derivative of the inside and put it on top. So what's the derivative of log x plus 4?
One over natural log of.
So just the inside, natural log, its derivative is 1 over x. And then the 4 is a constant, so
That goes away. So the derivative of natural log of x plus 4 is 1 over x divided by the natural log of x plus 4. Okay, so let's go to the natural log of e to the x minus secant. So on the bottom is going to be an e to the x minus secant. And then what we need is the derivative of that on top. All right, so what's the derivative of e to the x? Good, e to the x. Derivative of e to the x is e to the x. How about the derivative of secant? Good, it's secant tangent. All right, so there is what we get from logarithmic differentiation. So again, we need to multiply that y to the other side. So we get y prime is equal to 10 times 1 over x times the natural log of x plus 4 minus e to the x minus secant of x tangent of x over e to the x minus secant of x. And again, that's all times y. And so my original y was natural log of x plus 4 over e to the x minus secant of x raised to the 10th. So we'll put a box around it. And there's your derivative of that original function. So again, think calculus. Don't give me your moans and all that about algebra, because algebra is algebra. Think calculus. The calculus here was quick and easy, as opposed to otherwise we would have had to do chain rule with quotient rule inside of it. So again, I don't know if you see the power, but the more of these you do, the more you'll see the power of this. Fun fact, by the way, quotient rule, you don't need to know quotient rule. You never have to do quotient rule. Ooh, I think I just got some people excited. You never have to do quotient rule because you can always do logarithmic differentiation. Yeah, no, don't care. Check this out. Let me show you the quotient rule. What happens if we do it as log differentiation? And you see that we get the same thing. It can be faster and you don't have to remember that crazy formula anymore. But before I do that, we good? Good's not the right word. Are you seeing the steps? You seeing the process? All right, so there is, you can take a log for any differentiation, absolutely. And the only time it's going to help you, though, is if you have multiplication, division, or a power. Because if you just have add and subtract, the log's not going to help you. But no, legit, you can do it for anything else. Yeah, so those three, because those are the three log rules, right? When we multiply, we can split it apart. Divide, you can subtract it, and powers, you can bring the multiple out front. So it does help with not all chain. Because like, for example, if we did sine of something on the inside, that chain rule we still have to do. This one works for the general power rule. So only that one. So like if you got a square root of stuff, something raised to the 10th power, then it'll work. All right, so check this out. Let me just show you the generic quotient rule. And I'm going to show you how this would work if we did the log stuff. So let's go with just good old f over g. So I'm going to take a natural log. So I get the natural log of y equals the natural log of f of x minus the natural log of g of x. Since I've got division, it gets split into subtraction. Now if I differentiate, I'm going to get y prime over y equals f prime over f minus g prime over g and check it out. You just differentiated. I mean, you probably want to get it as y prime equals. Okay, well, so here you go. So y prime is equal to f prime over f minus g prime over g times the original y, which is f of x over g of x. But there you go. We just differentiated a quotient without using the quotient rule. No, nothing. No. I was hoping for at least one like, cool. Maybe. Yeah, there it is. Thank you. So that's what I'm saying. Like, because remember the quotient rule? Some of you may not. Or you get the little rhyme. Was it the low d high minus high d low square at the bottom and away you go? Well, that's what this is. If you were to distribute through, let me just show you the algebra. If you were to distribute through with this, you would get f prime over g, because the f of x is canceled in this piece, minus g prime times f over g of x squared. If we wanted to combine this into one, we'd have to get a common denominator, which would say multiply this first one by g of x. So you put that all together, you get f prime times g minus g prime times f over g of x squared. So it is exactly the same thing. It's just found without having to remember that formula. Well, take it for what it is. It's a way of not having to remember all these other rules. Log differentiation works really well anytime you have multiplication, division, or power. All right, so keep that in mind when you get these big, horrible looking things. Like if you ever see one of those and you go, ooh, I can do this, but it's going to require product and quotient and some chain. And start thinking, ooh, maybe log differentiation will make this faster. And like on an exam, let's say I put one of those on an exam, I'm not going to expect that you do all the algebra simplification afterwards, right? Like think about the examples I showed you and how like we had y prime equals and it took the entire length of the board. You get it there, I'm going to give you 100% because you found its derivative. I'm not going to care that you try to get common denominators and combine and blah, 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 because that's algebra details that we already all know how to do, right? We already all know how to do. So don't stress about that. Just think about the idea here is we need the derivative. What makes differentiation easier? Well, sometimes this taking a log trick is what it takes. Can make it way fast. All right, so I guess with that, I think our time's up. Oh yeah, time's up for today. So just to remind you, we do have a quiz next time. We have a quiz on Friday. We're back on schedule. We're going to have a quiz. I already gave you the last one off, so you don't get 2 off in a row. But this quiz, it's going to be on trying to remember where we are with derivatives. It's going to be implicit differentiation. Give me 1 second here. I want to make sure I'm telling you the right sections. All right, so it's going to be on sections 3.7 and 3.8. So 3.7 is inverse functions, derivatives of inverse functions, and 3.8 is implicit differentiation. Okay, so the quiz on Friday is on 3.7 and 3.8. I'll even write that down up here so people can see it in writing. So quiz Friday, 3.7 and 3.8. All right, so as always, the quiz will open up at 8:30. You have until 9:10 to get it in, and then we'll start Zoom session at 9:10. Okay, so with that, I'm going to go ahead and stop the recording.